How strong is this basic PLA filament? Is it strong enough for my project, or do I need to step up to something better like this PLA with carbon fiber? Does the carbon fiber actually make it stronger, or does it make it weaker? And by how much? Maybe none of these filaments is right. Maybe I should be using PETG. I've heard that that's stronger. Is it stronger? What about ABS? What about this other ABS? What about this ASA? Or maybe I need to step up to this carbon fiber nylon. Is this actually stronger than these other filaments? Is it actually stronger than other brands of carbon fiber nylon filament? And what about print orientation? How much of a difference does that make? What about temperature? What about speed? Are my high-speed 3D printers making my parts weaker? These are all really good questions, and they're not necessarily easy to answer. I have done some previous videos where I've tested some filaments just by printing parts and pulling on them with a crane scale until they broke, and I got a lot of comments that that was not very scientific, and that's because that was not very scientific. So I think it's about time that we build a proper tensile test machine, and I want to do it in the absolute easiest way possible. If you know anything about tensile testing, you no doubt recognize this shape. This is a tensile test specimen. I just 3D printed this on one of my printers, and it is a part that's shaped with a narrow neck in the center that should be the weakest area, so that if you grab the ends on this and pull, that's where the part will eventually break. So if we put this in a machine that has the ability to pull hard enough to break it and measure the amount of force required to do so, we can do some simple math with the cross-sectional area of this center neck down area, and it should tell us the tensile strength of the material in the as printed state. And we can print these horizontally on the bed, we can print them vertically so that the layer lines are either along the length of the break area or across the break area, and that will allow us to figure out the difference in the material properties in those two different directions. Now we just need a machine to do the pulling and the measuring. There are lots of different ways to do this. You can buy commercial machines for a few $100 to a few $1,000 that do this and do it very, very well. There are some DIY designs. There is one out there from CNC Kitchen that's open source from many years ago. Robert Cowan put one up recently. Several different YouTube channels have put up designs for their own tensile testers. I'm going to take a little bit different approach here today. I'm not looking to make the best tensile testing machine. I'm not looking to make the cheapest tensile testing machine. What I want is the easiest tensile testing machine. I want to get the job done with as little work as possible. So what do we actually need? Well, we've got our sample that we want to break. And we need some way to pull on it and some way to measure the force required to break it. Now, we have to hang on to this thing, and there are lots of ways to do that. The big commercial machines use clamps that hold on to the ends, but I don't want to machine any clamps. I don't want to go to that much trouble, so I opted to just put holes in the part, and we'll put a pin through that hole and use that to pull, just because that's the easiest thing to do. So then on one end of this, we need some kind of a force gauge. So we'll put a strain gauge here, and then we need to anchor that to something. And then on the other end, we need some way to pull on it. So we'll need to anchor that to something else that has the ability to move back and forth. So to move back and forth, we're going to need some kind of frame with some kind of linear bearing and something to apply the force. Let's say a screw of some kind to pull. And this is the basics of what we need. So we have to come up with a way to make the frame. Now I don't want to go out and get a bunch of materials. I don't want to spend a bunch of time machining. I want to just do the simplest possible thing that I can think of. And what this looks like to me is a vise, specifically a machine vise. So if we look at a typical machine vise, you've got a bed, you've got a fixed jaw, you've got a movable jaw that can move back and forth, and you've got a screw to move that movable jaw back and forth. And this is 90% of the structure of what we need. So we just need a way to attach a force gauge and attach a specimen, and we should be good to go. Now, for milling vices, you can buy soft jaws, and those jaws can be mounted either on the inside or on the outside. So if we get an extra tall soft jaw and mount it on each end on the outside here, That'll give us a place to mount our force gauge with our little display. And some kind of clamp with a pin, a clamp down here with a pin, and this will give us a place to put in our specimen. Then we just use the screw to open the vise until this breaks, and we measure the maximum force required to break it. This is the simplest thing I could possibly come up with. I already have the vise. I've got 2 of them over on my mill. I've got another one in a drawer. I can buy the soft jaws and then just drill a hole in them or something to mount the clamps. I can buy a force gauge with sufficient capacity at Amazon, and then that just leaves us needing to figure out something for these clamps. And we can either 3D print those or we can try to machine them out of metal. I'm hoping that a 3D printed part can be strong enough. Let's go into the computer and see what we can come up with. I spent a little bit of time wandering around on Amazon looking for a force gauge that could handle significant forces, and this is what I came up with. This is a cheap force gauge, but a force gauge in this kind of class is still going to run you around $200. So this has got a strain gauge that's capable of 5 kilonewtons, 5,000 newtons, or about 500 kilograms force, or about 1,100 pounds of pulling force. So the strain gauge comes with a couple of rings. These just thread in with M12 threads on each end, and when you pull on this, or if you compress this, it distorts the steel, and there's a strain gauge in here that measures how much it's distorted, and then there's a meter that can read that out. And importantly, this has a peak function, so we can let it read the force that's being placed on this, and when the sample actually breaks, the force will go down, and this should read the peak, and we should be able to see how much force was required to break the sample. Now, this is a 2 by 3 inch-ish block. It's actually metric, but it's pretty close. They're emulating a standard 2 by 3 by 1 inch strain gauge form factor. And again, it's just got the M12 threads on both ends. This should be pretty simple. We should be able to use the threads on one end to put in a clamp, the threads on the other end to anchor to a soft jaw in the vise, and we should be able to pull on this pretty much as hard as we want. I did go ahead and put this in one of my mill vices and compress it, and we can easily reach 5 kilonewtons with the mill vise, so the vise should be sufficient for this task. This force gauge should be sufficient for the task. I did do a little bit of testing on this, and it's not super accurate. It's, maybe 5% low is what I was reading. There are some potentiometers on the PC board inside of this thing. It might be something that I could calibrate. There's no instructions, no user serviceable parts inside. You're not supposed to do that, but I might fiddle with that at some point and see if I can make it a little bit more accurate. Still, 5% is fine. I'm not too worried about that for this application, especially since I'm mostly interested in relative measurements. Is this filament stronger than that one? If I print it faster, does it make it weaker? And those kinds of questions don't depend on having actual calibrated measurements. This is the vise that I'm planning to use. You really could use any kind of mill vise for this. This one happens to be a 6-inch Tagara 690X. This is Schar's house brand, and I've got a pair of these matched on the table of my mill here. But this is pretty much a clone of the very popular Kurt DX6. I actually have one of those in a drawer, and I thought about getting that out to use to build the tester, but I figured this thing is already bolted down here on the mill, and I'm lazy and I don't want to pick up that other vise. It's really heavy. So we're just going to go with this. Now, instead of actually making the parts and machining the parts to mount the sensors and the specimen holder onto the vise, I'm opting to just go with soft jaws. You can just buy these in a number of sizes, and these are just jaws that will bolt in place of the hardened jaws. These ones are made out of aluminum. These ones are extra tall. The idea with soft jaws is that you would machine shapes into these, especially for CNC machining, to hold irregular shaped parts. So these are essentially a consumable. But the advantage of these is you can just go buy them. 30 bucks or so, you can buy a set. These are 2.5 inch by 1 inch thick, and these will just bolt either on the inside or on the outside. And I'm planning to mount these on the outside of the fixed jaw and the movable jaw in the vise. So in terms of general layout, If I put this here, take the force gauge and attach it to that, we'll take this jaw off so it won't be in the way. Then we can attach the specimen holder here and pull in this direction. The other soft jaw goes here. Bring this in nice and close, and so if we have a holder here and a holder here with our specimen mounted in the middle, then we can just open the vise to pull on it. So overall size-wise here, I think this is going to work. And if this doesn't work, we can flip this around and put it on the inside and we can make it work that way. But let's go into the computer now and lay this out. I can download a model of the vise and let's figure out exactly what size everything needs to be. This design is simple enough that it may not really warrant a CAD model, but I like to make one anyway because it's really simple. I just downloaded a model of the vise from GrabCAD and quickly sketched up the other parts. And the benefit of having a model like this is that I can see in advance how everything is going to fit, and I can have confidence that I'm putting all the holes in the right places and I haven't made some terrible oversight. Now I am planning to 3D print these clamps. I'm just running M12 threaded screws into both ends. There's a set screw in this end and there's a cap screw in this end, and I've just captured an M12 nut inside the part. Now this makes it particularly easy to make this a 3D printed part because I can always swap it out later. If the 3D printed part turns out to not be strong enough, it's simple enough just to make a steel or aluminum block here with a slot and a hole in it and M12 threads in the back. So this will be a quick and easy thing to make because the 3D printer runs while I sleep. But then later, if I need something better or a better material, it's pretty easy to swap this out for something made in metal. Now I'm going to print these in PAHT carbon fiber. So it's a carbon fiber nylon material from Bamboo Lab. I'm printing this on the Bamboo Lab X1 carbon. Now the obvious way to print these parts would be standing up. In this orientation, they wouldn't need any support material. It would bridge easily over the top of this opening and the part would print and I wouldn't have any post-processing to do. The problem is that the layer lines would be going across the part and making it weak. So I want to print them laying down on the bed, which means I'm going to need support material in here. But because the X1 carbon can print multiple materials, I'm using the PAHT carbon fiber for the part, and I'm using the Bamboo Support G, their nylon support material, as a separation layer to make the support material break away easily. Now, printing these lying down, I have specified 10 perimeters, and so we get all of these extrusions that are going around the part. They're wrapping all the way around the nut, they're wrapping all the way around the pin, and this should give us maximum strength for pulling forces that are trying to pull this pinhole away from the nut. And I've got this set up so that it's using the support material just as an interface layer. So all of the support printed in here is in the same nylon material, but I've got a couple layers of the breakaway support on the bottom, a couple of layers on the top, so I can just grab this with pliers, break it out, and then peel off those two sheets of support material, and it should come out pretty clean. This is particularly important because if you have ever tried to peel away support material printed in nylon, it can be pretty gnarly, especially down in a slot like this. You'd like to maybe never get it all out. Now, since I bought pre-made soft jaws that already have the mounting holes in them, all we have to do is drill and counterbore a hole to mount the specimen or to mount the force gauge. Fortunately, I have another vise over here, and I can easily just put a parallel in that vise, extend it over, and that gives me a stop. Now, unfortunately, that's the largest drill I have, which is a 1/2 inch, and the hole is still not big enough to get the pilot for my M12 counterbore through there. So we are going to have to bore. Nice. Plenty of room to adjust. That will work. There we go. Those are ready to go. To make the pins to secure the samples in the tensile tester, I'm planning on just using M6 and M5 screws. I'm actually not sure which one I'm going to need. I've got both designs, so I've got a couple screws of each in here, but I need to shorten these. Now I could use shorter screws, but then they would have threads up in the area where I've got force bearing on them, and I don't want that. So I got ones that are long enough that have enough of a smooth shaft here, smooth shank, that I can just shorten them and just use that as a pin and cut off the thread. So I'm going to do that here in the lathe. Now I can only do the 6mm ones right now because for the life of me, I cannot find my 5mm 5C collet. No idea. I've looked everywhere. It just vanished. I guess I'm going to have to buy one, and then of course I'll find it. Now to hold this in the lathe, I'm going to use a 5C collet, and I'm going to put this in through the collet from the back. That'll give me support right up to the point where I have to cut it, and it'll give me support on the smooth part of the shank so I'm not trying to grip on the threads. Now to measure the length, I can, with a thin scale, reach through the slot in the collet, and I can reach back and I can feel the head of the screw, and that'll give me my reference so that I can set my tool and cut this off. I'm going to start with a parting blade. This might not be a great idea just because the diameter is so small, but we're going to give it a try. If I break the blade, then we'll just cut it with a hacksaw and turn it to length. Honestly, that went a lot smoother than I expected. Now I'm just going to zero the tool by eye here. That looks good. Let's smooth this thing out. Let's see how close we got. 25.36. 25.4 would be exactly an inch is what I was shooting for, so I will call that good. .32, 25.33. Close enough. Now, if only I could find my 5mm collet. Arrgh. Okay, we've got our modified soft jaws. We've got our 3D printed specimen holders. We've got our pins. And we have a box of hardware that I paid way too much for at my local hardware store. So let's put this thing together. We'll start with the 5mm pin version just because I want to see how much force it takes to break those samples, and then we'll work our way up. Ideally, I want to be in the sort of sweet spot for the range of the force gauge that I have. If we're too far down at the bottom or if we're bumping up against the top, that's not really going to work. I want to be kind of in the middle of the range, so we've got lots of headroom, but we've also got lots of resolution, so we will just have to see what happens. Let's see, we want this to lay over this way. So we'll use a set screw here. Okay, so that's not quite right. It doesn't line up, so I'll just rotate the nut inside the part here. And that should make it line up properly. Perfect. Okay, the goal here is to set this so this is a little bit off of the jaw, so it's not interfering with it, it's not scraping on it. Should clear this jaw, this should be above this jaw. And we should be able to close it far enough to put in a specimen. That looks good. Grab our first victim here. And we should be able to pull on that. Make it the force gauge. We've got a sample in here. I actually don't have any idea what this material is. It's just something that I printed out when I was playing around with the design of the test specimen. Got it between our 5mm pins here. Got the force gauge set up. I've got it zeroed. I have it set to newtons. I had to check that because the last time I did a test I had it set to pounds and said it was set to newtons. It's actually set to newtons. Set this into peak mode. Actually turn that off and put a little force on it so you can see the gauge is moving. There's 58 newtons. Back that off. We go back to 0. Nice. Put it in peak hold mode. And we'll just pull on this until it breaks. Let me get some safety glasses. Safety glasses, you never know what might happen. And I have no idea what's going to happen here. Let's just pull on it until this thing breaks. And what broke? This actually broke through the eyelet, so that is not ideal. That is not what I had in mind. Let me grab another sample, but we had 1,435 newtons. That is a totally reasonable, respectable load for something like this. This goes to 5,000, so that seems pretty okay. Let's find some other samples. Okay, I've got 2 bags of samples here. These are both ABS. These ones were printed vertically, and these were printed horizontally on the X1 carbon. So let's pull a few of these, see if we get consistent results, and see what they are, and see if there's a difference between the horizontal and the vertical. There better be. Okay, let's start with the horizontal samples. And this is just Bamboo Labs, their basic ABS printed on the X1 carbon. And we'll just pull until it breaks. Okay, and that actually broke through the neck down area. 1,186. Grab another one. $11.27. That's pretty consistent. And let's do one more. $12.01. Okay, so that's 11.27, 11.86, and 12.01. That's actually pretty consistent. I'm pretty happy with that. So those are the horizontally printed samples. Now let's try some of the vertically printed ones. This is the same material, printed on the same machine with the same settings, except these were printed in the vertical orientation, so the layer lines go across the sample. So I would expect these to be quite a bit weaker. Let's see. There you go. 389.4. Now that one actually broke through the end. So I think I'm going to have to go back and redesign these samples and put some more meat across there. And that failed in exactly the same place. And let's try one more. And that also broke through the eye. Okay. So I definitely need to redesign my sample because at least in the vertical orientation, they are not breaking the way I want them to break. That is not what I had in mind. Okay, I was playing around with this a little bit more off camera, and I've got one other material that I wanted to try here. This is the Bamboo Labs PLA Basic. Sorry, Bamboo Lab PLA Basic. This is the horizontal orientation. Let's pull on that. $16.85 newtons, and you can see it broke exactly where we want it to break. And let's try one more, just to make sure that wasn't a fluke. $17.17, which is way stronger than any of the other materials I've tried so far. Now let's try some printed in the vertical orientation. And just see, these should be weaker, but how much weaker? Okay, that split through the eyelet at 734. And through the eyelet again at 952, though that's pretty respectable. It means this across the layer lines on a, I believe this is a 6x5 cross section, held 952 newtons. That's a lot of force. And of course it broke up here. I'll have to fix that design. Okay, I've gone back through and redesigned these parts again, and I've just added even more meat around the pinhole here. Though I'm starting to wonder if maybe I'm on the wrong track. The center section here that I want to break is being pulled straight, so the pressure should be even across the entire cross section here, and it should pull until it snaps. But because the force is on the pinhole in the center and not on the outside, there's going to be a force concentration next to the hole, and this whole top section on this side is going to be under a bending force. And so it's going to tend to just unzip the layer line across. So instead of getting the benefit of the entire strength of the whole width here, the pressure in the center is going to cause that to tend to unzip, and it's going to cause that to be the failure point when printed in the vertical orientation rather than here in the center. So this may be the reason why professional tensile testers all use clamps, and I may have to move to clamps, but I've added more meat. Let's give it a try and see what happens. Okay. And even with more meat, it's still broke on the end there. That one broke in the middle. That's 1 out of 4. Okay, there's 2 of 4 that broke in the way I wanted them to break. Well, that is disappointing. It might just be that using a pin is not going to work in parts in this orientation. You can see with this break that that you can see where the stress built up on this side right here, and it broke there first and then just unzipped. And then of course the force all got released and just ripped off the other half. So I'm starting to get really skeptical, even though I've seen other designs that use this. I'm starting to get skeptical about the appropriateness of the pin as an anchoring mechanism for at least vertically printed tensile test specimens. So what have we learned here? Well, first off, I think the decision to use the mill vise as the framework for a pull testing rig was absolutely inspired. We got all of the structure and the ability to handle very large forces with almost no effort. Now, the one drawback here is that there is a little bit of jaw lift when we're pulling with the jaw rather than pushing with it. I think that could probably be solved by taking the vise apart and flipping the nut and the moving jaw around so that we get the cam action to pull the jaw down when it's pushing in this direction. I'm not certain of that. It's something I might play with if I wanted to dedicate a vise to something like this, but just for temporary use for, just running some tests, I really don't think it matters that much. The second thing that I'm really happy with is the choice of the carbon fiber nylon material for these specimen grips. I am really impressed with the performance of this stuff. We put, 2 kilonewtons on this in our testing so far. That's 200 kilograms force, that's 440 pounds. That's a lot of force, and these didn't even show any signs of stretching or cracking or any kind of failure that I can see. I'll keep pushing them, we'll see what they can do. The benefit of making a 3D printed part here instead of making something out of steel or aluminum is that it was really quick and easy, and I got a chance to put something together and learn from it. And what I learned, of course, is that using a pin to hold these samples may not be suitable. It just might not be possible to use a pin in a vertically oriented sample and hold these things and get them to break at the neck down region. I mean, I could try a bunch of things with the design of the specimen, but I think I need to revisit how these things are held. But again, we wasted no time in order to learn that. I just sketched this up, sent it to the printer, and I got to try it with very little effort. Now, the big boys use wedge-style clamps, and I know there's some people out there that have made them, but I didn't want to spend the time doing that because the whole point of this was quick and simple and learn quickly. And I think I accomplished that, and we'll see. I may play around with some other 3D printed designs, or I may just decide to test only in the horizontal orientation if that meets the needs for what I'm trying to learn with it. We'll see what the future holds. If you enjoyed this video, give it a thumbs up. Feel free to subscribe to the channel, and maybe think about supporting the channel over on Patreon. Patrons get access to files and CAD models for all of my projects, and the files for this project will be up there as well. I don't know why you would want them, but if you do, they're there. And feel free to leave me a comment and tell me what I did wrong, or more importantly, tell me what I could do better. If you've got an idea for solving this problem with the specimens breaking with a very simple clip with pins or some other simple structure that doesn't require machining, I'm all ears. I'd love to hear about it. Or if you think really the wedge clamps are the only way to go, let me know that too. I'd like to hear it. Thank you for watching.